The location of the flinder bar. Now you see we have the binnacle here. This is the compass bowl, and then we saw in permanent B that we use fore and aft magnet placed in these trays. Now the flinder bar is placed in this housing. You see this cylindrical housing which is there. It is fitted forward of the compass. So why it is fitted forward of the compass? Because it is compensating or correcting the magnetism of the funnel. The funnel is fitted aft of the compass. On a normal merchant vessel, you will have the funnel aft of the compass. So to counteract it, the flinder bar is placed forward of the compass. You can see the flinder bar in this particular diagram also. This cylinder which you see represents the flinder bar. You can see it is mentioned here. So this is the housing which you are seeing. This is the casing, and in this casing inside we have the flinder's bar. The use of the soft iron bar and the wooden bar for filling up the flinder's bar. So you see this is the flinder bar present on a ship, and this is basically the casing in which the bar would be placed. The maker supplies us a soft iron bar in these dimensions. You see one piece is for 305 mm, the next one is 152 mm, 76, 38, then two pieces for 19 mm. And along with the soft iron bar, he also provides a wooden bar of same dimensions. You see we have the pieces with exactly same dimensions. So first of all, compass adjuster evaluates what length of the flinder bar he requires. Let us assume that on a particular ship, the compass adjuster has ascertained that he needs to use these two pieces, 305 mm and 152 mm. What he does now is, leaving these two pieces, 305 and 152, 305 and 152, he will pick up all the other pieces of the wooden bar. So you see all these pieces with a green tick mark, other than the ones which are required, other than 305 and 152, he will pick up all the wooden pieces, 76, 38, 19 and 19. And he will pick and drop these pieces in the flinder bar casing. So let us put these pieces here. You see all these four pieces coming here. 19 mm, 19 mm, 38 mm and 76 mm. All these four pieces coming here. These are the wooden bar pieces. Now once these wooden pieces are placed at the bottom of the flinder bar casing, he now picks up the required soft iron pieces, 152 mm and 305 mm, and he drops these pieces into the flinder bar. So you can see this 152 mm piece and the 305 mm piece dropped in the flinder bar, and now you can see the top end of the soft iron bar will be in level with the compass card or as required. So the bottom portion is filled using the wooden pieces, thus making the flinder bar correction. Our first coefficient, that is coefficient A. Coefficient A is a deviation which remains constant in name as well as magnitude on all the headings and is further divided into two parts. These two parts are number one, real A, and number two, apparent A. Now, if you remember the formula which I had shown you, the formula for deviation, in that formula we saw that this coefficient A is not connected with the ship's course in any way. Indirectly, that means that whatever be the course of the ship or whatever be the heading of the ship, the value of coefficient A is not going to change. And you see exactly that is what the definition also tells us. Coefficient A is a deviation which remains constant in name as well as magnitude on all the headings. The vessel can continue to change its heading, and the deviation which is generated because of coefficient A does not change at all. It has two components, and it can be divided into these two components. One is called as real A, another is called as apparent A. What is this real A part of the coefficient A? It is a constant deviation on all the headings caused by induced magnetism in unsymmetrical pairs of horizontal soft iron. I will explain this to you in detail by showing this kind of structure in the diagram. So for now, just understand it is caused by induced magnetism in unsymmetrical pairs of HSI, horizontal soft iron. So the cause of real A is the horizontal soft iron on board. The second part, which is called as apparent A. Apparent A is a constant deviation on all the headings, which is caused by factors other than the magnetic field. So up to here clear, beta? Any doubts? Bolo beta. Let me now show you the kind of structures which may generate coefficient A on a particular ship. Now we have seen that coefficient A is generated because of unsymmetrical pairs of horizontal soft iron. Now horizontal soft iron HSI can be present in two orientation. We can have a fore and aft horizontal soft iron, something like this one. This is horizontal soft iron in the fore and aft direction, and we can also have horizontal soft iron in the athwart ship orientation. You now see another horizontal soft iron which has a athwart ship orientation. So the first thing to note is that coefficient A require a pair. Pair means there should be a combination of fore and aft as well as athwart ship horizontal soft iron. The second thing which is required is that these horizontal soft iron should be unsymmetrical. Now what do we mean by unsymmetrical? If you look closely, the fore and aft HSI which we have is present only forward of the compass location. The circle which you see in the middle of the ship is representing the compass, the binnacle, and the HSI in the fore and aft orientation is only present forward of the compass, and it is not there aft of the compass. This kind of a HSI is known as unsymmetrical HSI. Likewise, this athwart ship HSI which you see is present only on the port side of the compass, and it is not present on the starboard side of the compass. So both these HSI are unsymmetrical. That means they are present only on one side of the compass, and there is a pair present, means both fore and aft and athwart ship HSI are present. This kind of a combination, if it is present on a ship, will generate coefficient A. Now, usually we do not see any kind of these structures on a normal merchant vessel. You will always have symmetrical HSI. So that is exactly the reason why coefficient A is absent on most of the normal merchant vessels. Such a configuration of horizontal soft iron on board a ship, so these kind of structures are present. How do they result into a real A coefficient? Or in other words, how do they generate a deviation which is constant irrespective of the heading of the ship? Whichever heading the ship goes, the deviation generated by these structures remains constant and does not change. So let us try to understand it. Now this is understood by making a deviation diagram. For every coefficient, we will be making a deviation diagram like the one you see on the screen now. We have the ship on different headings: north, northeast, easterly, southeast, south, southwest, westerly, and northwesterly. So cardinal and intercardinal heading, the ship is shown on these 8 headings. And in each of these headings, we are going to analyze that how do these horizontal soft iron structures, it is an unsymmetrical pair of horizontal soft iron structures, they generate the deviation which does not change. So we will first try to understand how do these structures affect our ship, and second we will try to see that how does this effect remain same irrespective of the heading of the ship. So let's try to concentrate our attention with the ship on the northerly heading. The ship is on a north heading. You can follow the laser pointer. This is the diagram which we are going to see or understand in detail. Now the ship is on a northerly heading. We have these 2 soft iron structures. One, a athwart ship beam, which is only present on the port side of the compass. And we have a fore and aft longitudinal, which is present on the starboard side, only forward of the compass. It is not present aft of the compass. So we have combination number 1, which we saw in the previous slide, a unsymmetrical pair of horizontal soft iron structures. You see this big blue color rectangle on top. This represents the north magnetic pole of the Earth. We are aware that the north magnetic pole of the Earth has blue polarity. And you see this red color rectangle at the bottom. This represents the south magnetic pole of the Earth, and we are aware the south magnetic pole has a red polarity. Now we know that the magnetic lines of force, they come out of the red pole and they go into the north pole. So the magnetic lines of force coming out of the red pole going into the blue pole. So in this particular diagram, you will see that the magnetic lines of force are going vertically upwards from the red pole to the blue pole of the Earth, going vertically upwards like this. Now with the magnetic field of the Earth going vertically upwards, it will affect both these structures. It will affect the fore and aft longitudinal also, and it is going to affect the athwart ship beam also. Now first thing to understand is that these are soft iron structures, so they do not have any permanent magnetism. There is no permanent magnetism in these structures. But being soft iron structures, they can get induced by the magnetism or magnetic field of the Earth. Now the magnetic field lines are going vertically upwards. If you concentrate your attention to the athwart ship beam, this athwart ship beam is not oriented or aligned in the direction of the magnetic field. It is at right angles to the magnetic field of the Earth. Used magnetism, I told you that there is minimum induction or zero induction, negligible induction, when the soft iron structure is misaligned with the inducing field. The inducing field in this direction is in the north-south orientation, and this athwart ship beam is in the east-west orientation. The vessel is heading north, so the beam is in east-west orientation. So this beam is at right angles to the inducing field or the magnetic field of the Earth. Now being at right angles, no induction happens. No magnetic field induction happens here, and the athwart ship beam does not acquire any magnetism. There are no poles which are generated. Let's now concentrate our attention to the fore and aft longitudinal. The fore and aft longitudinal, if you look carefully, is aligned exactly in the same direction in which the Earth's magnetic field lies. The magnetic field lines are in the north-south orientation. The fore and aft longitudinal is also exactly in the north-south orientation. So the fore and aft longitudinal is perfectly aligned with the magnetic field. And this tells us that there will be maximum induction in the fore and aft longitudinal. Maximum induction. So we know the fore and aft longitudinal having maximum induction will become a strong magnet now. Let us now understand the direction of the poles which are generated. We see the magnetic field lines are coming out from the red pole of the Earth and going into the blue pole. So this tells us that these magnetic field lines will be entering into the aft end of the longitudinal. If they are entering into the aft end of the longitudinal, wherever the lines of force enter, that end gets a blue polarity. Wherever the magnetic lines of force are entering, that end of the magnet has a blue polarity. So that's why you see the aft end of the fore and aft longitudinal has a blue magnetic pole. And these lines of force going from south to north will be coming out from the forward end of the longitudinal, the forward end. Since they are coming out of the forward end of the longitudinal, you will see that the forward end of the longitudinal acquires red polarity. So this is the reason why you see in the diagram, the aft end of the longitudinal has blue polarity and the forward end of the longitudinal has red polarity. So we now understand the different poles generated on the fore and aft longitudinal. The induction or induced magnetism of the horizontal soft iron structures by the Earth's magnetism. Let's now try to see that at different headings, what is the deviation which is generated because of this induced magnetism. So as you can see in the diagram, at every heading, they indicate to us that it is a easterly deviation. You see north heading, northeast, easterly, southeasterly, southerly. On all the headings, they are denoting that the vessel has a easterly deviation. And in the definition of coefficient A, we have seen that it generates a constant deviation irrespective of the heading. So we will try to see now how does this deviation remain constant over all the headings. Let's first of all try to understand how this easterly deviation is generated with the ship on northerly heading. So what I'm going to do is I'm going to zoom in into this diagram with the ship heading north. We are aware that we have a fore and aft longitudinal and a outward ship beam. There is no induction on the beam right now because it is at right angles to the Earth's field, and there is maximum induction in the fore and aft longitudinal. So let's now try to zoom in into this. So here on the left side, you see a zoomed in diagram with the ship heading north. Let's first make the magnetic compass on this ship. Now we know the magnetic compass is basically a magnet, and the end which points towards the north is the red end of that magnet. So let's show our magnetic compass. You can see it here. The north end of the magnetic compass is having a red polarity. You see the red color, and the south end is having a blue polarity. So this arrow which you see in the zoomed in diagram of the ship now represents the magnetic compass. And we have a longitudinal which is to the starboard side of the compass, and it is forward of the compass location. It is not present aft of the compass location. So you can see this longitudinal in the zoomed in diagram now, and it is to the starboard side of the compass and is extending to forward of the compass. Now we have already seen that this particular end, the aft end of the longitudinal, acquires a blue pole, and the forward end of the longitudinal acquires a red pole. This is a soft iron structures, and these poles are acquired as induced magnetism, which are generated by the magnetic field of the earth. Now, whenever we bring a magnet close to our compass, every magnet has two poles, a red and a blue pole. We cannot have a single pole in a magnet anywhere. Even if you break up a magnet, the broken ends immediately acquire the polarity. You cannot have a single pole at any point. Now, whenever you bring a magnet close to the compass, it has both the poles, the red as well as the blue. Now, which of the poles is going to affect the compass? Always, in all the conditions, that poles affect the compass which is closer to it. Because as you go far away from the pole, the magnetic field or its strength or its power reduces. It is inversely proportional to square of the distance. Means if you increase the distance by twice, the magnetism or magnetic field strength of the pole goes down by 1/4. So whenever you bring a magnet close to the compass, that particular pole which is closer with respect to the other has its effect on the compass. Now in this particular case, the longitudinal is having two ends. One of the ends is very close to the compass, which is having a blue polarity, whereas the other end, for clarity, I have exaggerated a bit and taken it out of the ship's hull. So the other end of the longitudinal is close to the bow of the ship, which is much farther away as compared to the blue pole. So in this case, blue pole is the one which is going to have its effect on our magnetic compass. Now, how does this blue pole affect our compass? The effect of this blue pole onto the red end, that is the north end of the compass, will be attraction. Because we are aware that opposite poles of a magnet attract each other. So this blue pole of the fore and aft longitudinal is going to attract the north end of our magnetic compass or magnetic needle. So when it attracts the north end towards it, the compass is going to deviate to the right side. Looking at the diagram, it is going to deviate to the right side, and that is easterly side. With the vessel heading north, the right side is easterly direction, so a easterly deviation is generated. Also, you can see this blue end is also going to interact with the south end of the compass. The south end of the compass also has a blue polarity. Now we know that the same poles of the magnet repel each other. So this blue pole of the longitudinal is going to repel the blue pole or the south end of our magnetic compass, again generating easterly deviation. The compass needle is going to swing clockwise, which is easterly deviation. So that is why you see they have mentioned here as easterly deviation. Try to understand the deviation generated on 090 heading. We take the ship on 090 heading and we try to understand what is the deviation generated. Now you see when the ship is heading 090, the fore and aft longitudinal is heading in the east-west direction, and it is now perpendicular to the Earth's magnetic field. Earth's magnetic field is in the north-south orientation. With the longitudinal in the east-west orientation, it is at right angles to the Earth's field, and it is totally misaligned with the inducing field. That is why no induction on the fore and aft longitudinal. On the other hand, the outward ship beam is now perfectly aligned with the magnetic field of the Earth. The Earth's magnetic field is in the north-south orientation. The outward ship beam is also in the north-south orientation. Perfectly aligned, it generates maximum induction. So you see onto the starboard end of the beam, a blue pole is generated because this is where the lines of force are entering. The lines of force come out from the red pole of the earth and they go into the blue pole of the earth. So the starboard end of the outward ship beam acquires a blue polarity and the port end of the outward ship beam acquires a red polarity. Now to see its effect, let us now zoom into this particular diagram of the ship. We can zoom in and see the effect in detail. You can see the zoomed in diagram on the left side now. The vessel is heading in the easterly direction. The fore and aft longitudinal does not have any magnetism, so that's why it is not shown in this diagram. There are no poles generated there. The outward ship beam is present forward of the compass only on the port side. You see, it is unsymmetrical, so it is not present on the starboard side of the compass, it is only present on the port side of the compass. Being unsymmetrical was a requirement of generating real A deviation. Now we have seen the south end of the outward ship beam acquires a blue polarity. This is where the lines of force are entering. And the north end of the outward ship beam acquires a red polarity. Now the north end of the beam is close to the ship side and is far away from the compass, whereas the south end of the outward ship beam is very close to the compass location. It's very close to the compass location. So blue is what affects our compass. The ship is heading in the easterly direction. Compass always points in the north-south direction. So compass is pointing in this particular direction only. And we have a blue pole to the east of the compass. This blue pole attracts the red end or the north end of our compass needle, and the blue pole repels the blue end of the compass needle or the south end of the compass needle, again making the needle swing clockwise, generating a easterly deviation. So you can see again a easterly deviation is generated. So whether the ship is on north heading or the ship is on easterly heading, in both the cases, easterly deviation is generated. With the ship heading in the northeasterly direction. So with the ship heading in the northeasterly direction, how does the deviation behave? Let's zoom into this diagram of the ship. So on the left side, you see the zoomed in diagram of the ship. Compass as usual placed in the center line. Irrespective of what is the direction in which the ship is heading, the compass needle is always going to point north and south. The north end will be the red end of the compass and the south end will be the blue end of the compass. Now we have a longitudinal, fore and aft longitudinal to the starboard of the compass. So you can see on the starboard side we have a fore and aft longitudinal which is only forward of the compass. It is not there aft of the compass. We also have a outward ship beam. The outward ship beam is forward of the compass and only to the port side. You can see the outward ship beam is only to the port side of the compass. It is not present on the starboard side. Now I have taken the far ends of the longitudinal and the beam out of the ship's hull just to make the picture a little more clear and easy for understanding. Now in this case you see the Earth's magnetic field coming from south to north is going to induce both these structures because both of these structures are now at a 45-degree angle to the Earth's magnetic field. They are neither fully aligned nor misaligned. They are partially aligned with the magnetic field of the Earth. So there will be partial induction on both these structures. That is the longitudinal as well as the beam. Partial induction on both of them. So the poles generated will have partial power. And now you look carefully. The blue pole is generated in the longitudinal as well as the beam, and this is the pole which is closer to our compass. The red poles generated are far away from the compass. So blue poles are the one which are going to affect our compass. Now the blue pole of the authorship beam is closer to the red end or the north end of the compass, and it is going to attract the compass towards it. Whereas the blue pole in the longitudinal is close to the south end of the compass, which is again blue, and both being the same polarity, they are going to repel each other. And you will see, even though there are two poles, they are both trying to swing the compass in the clockwise direction again. So you see, the compass has to swing clockwise again, generating easterly deviation. Now, one doubt may arise that since there are two blue poles now, the deviation generated will be more powerful, but that is not the case. Reason being, even though two poles are generated, but both of them have partial power. Why the power is partial? Why their strength is partial? Because they are not perfectly aligned with the magnetic field of the earth. Both the longitudinal and the authorship beam are partially aligned, making these poles partially powerful. So when both these poles add up, they generate the same easterly deviation which was generated on 000 heading and 090 heading. So you can see, irrespective of the heading on which the ship is, the deviation generated remains the same. So I hope it is clear now, beta.
Sir, for this northwest direction, HSI.
Yeah. Correction of real A. How do we correct this coefficient? The correction of real A is generally not attempted, not done. The reason for it is, number one, it is very rare on a normal seagoing merchant ship that a coefficient A will exist, because these kind of soft iron structures are not present on the ship. Whatever soft iron structures are present, they are symmetrical about the compass location. Even when it is present in some ship, it is likely to be very, very small. So this is the reason why we do not attempt the correction of real A. What is done then? Since the deviation generated is constant on all the headings, it can be applied as an index error. So you will see that on a ship where real A is present, the real A value will be mentioned separately in the deviation card. Like, let us say, for example, the deviation card will tell you that the real A correction or index error correction is 1 degree east. So whatever deviation you obtain from the curve, you add 1 degree east to that deviation and it will give you the resultant deviation. So deviation being constant on all the headings, is it applied as a index error, and the real A is not generally corrected. Now the second component of coefficient A, which is known as apparent A, is basically the constant deviation on all headings caused by factors other than the magnetic field. So any reason, any cause other than the magnetic field which leads to a constant error on all the headings will come under apparent A. There can be numerous reasons for generation of apparent A. Some of the examples, some possibilities which could lead to this kind of an error. You can have the magnetic needles of the card not parallel to 180 degree direction of the card. Now this is a manufacturing defect. You can visualize a card is being printed. The magnets are to be fitted exactly in the 000180 direction. But if during the construction of the card, the magnets are fitted slightly at an angle, let us say 002 and 182 direction, So there will always be a slight error which the compass will show. This has got nothing to do with magnetism, so this falls under apparent A. That's a manufacturing defect in the card. Sometimes we see there is a lubber line which is fitted on the repeater. If the lubber line is not parallel to the ship's fore and aft line, so whenever you read that lubber line to get the heading of the ship, there will be a constant error. This has got nothing to do with magnetism, and it's also a manufacturing defect, so it falls under apparent A. Other reason could be constant error in observing the bearings when the compass is initially adjusted. For example, there could be an index error in the azimuth mirror leading to wrong deviation card. So when that wrong deviation is applied, you will get an error. So that's also a non-magnetic reason. Further reasons could be error in computing the magnetic bearing when the compass was adjusted, rapid swinging of the vessel when observing the bearing for compass adjustment. It is recommended that whenever we are doing the compass adjustment, the vessel should not be swung rapidly. It should be steadied on a particular heading before noting down the deviation. Or are angles worked out wrongly leading to error in the calculated bearing? We usually obtain the compass error by using the azimuth, calculating the azimuth by ABC method. So if the method has been worked out wrongly, it will lead to a wrong deviation being noted down. And if we use that wrong deviation, it will give us wrong bearings or wrong heading of the ship. So there could be many other reasons also. Any reason other than magnetism which leads to a constant error on all the headings falls under the category of apparent A. For the correction purpose, the value of coefficient A can be easily obtained as the mean of deviation on at least 4 equidistant headings. What does that mean? Let us take the ship on a northerly heading and note down the deviation. Let's now take the ship on a easterly heading, note down the deviation, then southerly heading and westerly heading. So all the 4 cardinal headings, we swing the ship, take it to 4 cardinal headings, and we note down the deviation on these 4 headings. Now, once you take a mean of these 4 deviations, it gives you the value of coefficient A for that particular ship. Practically, this is done using 8 deviations on cardinal and intercardinal headings. Taking this value in 8 deviations gives you more accuracy. So practically we use the deviations on cardinal and intercardinal headings and take a mean. Now you can easily test out this method or try out this method using this formula. This is the same formula which I showed you. Deviation is equal to coefficient A plus B sine cos plus C cos cos plus D sine 2 cos plus E cos 2 cos. So in this formula, if you put the cos as 0, 0, 0 and get the result, then second time you put the value as 90, third time you put the value as 180, fourth time you put the value of cos as 270. Now, once you get the answers and you take a mean, you will see that all the other coefficients B, C, D and E will get cancelled out. The only coefficient which will remain is coefficient A. Now let's move on to the second coefficient, that is coefficient B. The definition says coefficient B is the maximum value of the semicircular deviation which varies as the sign of the compass course. Now in the formula which I gave you, in that particular formula, what is that part which is proportional to or which varies as sign of the compass course? It is the second part of the formula. that is B sine course. Now the maximum value of that deviation is what is coefficient B. So you see this definition has been picked up, or you can easily remember this definition basis the formula. Coefficient B is the maximum value of the semicircular deviation which varies as sine of the compass course. That part of the deviation which varies as sine of the compass course, the maximum possible value what it can have is what is coefficient B. Now, what is the meaning of semicircular deviation? Now we know one circle is 360 degrees. So if a deviation carries the same name over the entire 360 degrees, if it is east and it remains east for the vessel heading on entire 360 degrees, it is called a circular deviation. A deviation which is of one single name for a semicircle, that is 180 degrees, and in the other semicircle, the remaining 180 degrees, it gets a opposite name. It is called as a semicircular deviation. To give you an example, let us say on a particular ship, you observe the deviation from heading north to south. It is easterly deviation. And when the ship heads from south to southwest, that is 180, 190, 270 up to 360 in the southwest and northwest quadrant, the deviation is westerly. So you see now for 180 degrees, the deviation was east. For the next 180, it has changed to westerly direction. Such a deviation is called as a semicircular deviation. Deviation changes after every 90 degrees. For the first quadrant, the northeast quadrant, the deviation was easterly. For southeasterly quadrant, the deviation becomes westerly. For southwesterly quadrant, it again easterly, and for northwesterly quadrant, it becomes westerly. Means it changes after every 90 degrees. It is known as a quadrantal deviation. So semicircular deviation means that for 180 degrees out of the total 360, it will have one particular name, either east or west, and for the remaining 180 degrees, the name is going to is the horizontal fore and aft component of the ship's magnetic field. Go ahead, beta. Horizontal fore and aft component of the ship's magnetic field is caused or generated by permanent magnetism of the ship as well as induced magnetism of the ship. So the contributing factor for coefficient B are both permanent magnetism as well as induced magnetism. The part of coefficient B generated by permanent magnetism is called permanent B, or in short PB, Papa Bravo. And that part of the coefficient B which is generated by induced magnetism is called induced B, or in short form IB. Let's now see the cause of permanent B on a ship. Now we are aware, concentrate your attention to the diagram, first diagram on the left hand side where the laser pointer is right now. Let's assume that this ship is being built in the yard on a northerly heading. If it is built in a northerly heading, the lines of force will be entering from the stern of the ship and leaving from the bow of the ship, giving the stern a blue polarity and the bow a red polarity. Now, if the ship was built on a southerly heading, then in that case, you will have a blue bow and a red stern. Now, these poles which are generated are permanent poles. So depending upon whether the ship was built on a northerly heading or a southerly heading, you will have a blue bow or a red bow. Now, when the ship has magnetism in this particular way, it has a blue bow and a red stern. How does this magnetism affect our compass? If you look carefully, this is the permanent magnetism of the ship in the horizontal fore and aft direction. What causes permanent B? So let us see its effect on our magnetic compass. Now this is a diagram which is showing us, this is the deviation diagram for coefficient B. It is showing us a ship which has a blue bow. You see everywhere at the bow we have a blue pole, and this ship is having a red stern. So this tells us that this particular ship was built on a southerly heading. So just now, as we saw in the previous slide, a ship which is built on southerly heading will have a blue bow, the lines of force will be entering there, and a red stern. Now, how does this permanent magnetic field of the ship in the horizontal direction, fore and aft direction, going to affect our compass? Let us see it heading by heading. Now, with the ship heading in the northerly direction, we have a blue bow and we have a red stern. The compass needle is shown in the middle of the ship. We know that the end of the compass needle pointing towards north is the red end, and the one pointing towards the south is the blue end. So we have the compass needle. Now when the ship is heading north, these blue and red poles of the ship are exactly north and south of our compass needle. So being exactly north and south of the compass needle, they do not generate any deviation at all. So there is no deviation on the northerly heading. Let's now assume the vessel has moved to a northeasterly heading in this particular direction. Now the blue pole has gone northeast of the compass, and this blue pole is going to attract the red pole of our compass, and the compass is going to deviate towards east. So you have a easterly deviation. The same thing happens with the red pole. The red pole of the ship, permanent magnetism, red pole of the ship has gone to southwest of the compass, and it attracts the blue end of the compass towards it, giving the compass a easterly deviation. So you can see now on a northeasterly heading, a easterly deviation is generated. When the ship goes to a easterly heading, 090 heading, now you see the blue pole is to the east of the compass and the red pole is to the west of the compass. They are at right angles to the poles of the earth, and now in this location they generate maximum deviation. The blue pole at the bow attracts the north end or the red end of the compass towards it, and the red pole at the stern attracts the south end of the compass towards it, giving it maximum easterly deviation. When the ship heads in a southeasterly direction, the blue bow goes to southeast of the compass, and this blue bow repels the blue end of the compass needle, that is the south end of the compass needle. Similarly, the red pole of the ship at the stern repels the north end of the magnetic needle, again giving it a easterly deviation. But the magnitude of the easterly deviation starts to reduce now because the ship's poles are coming in line with the magnetic field of the earth. Maximum deviation is generated when the ship's poles are at right angles to the magnetic field of the earth, which happened on easterly heading, and minimum deviation is generated when the poles are aligned with the poles of the earth, which happened on northerly heading. If ship pole and earth pole are aligned, there will be no deviation at all, And if the ship's poles and earth poles are at right angles, there will be maximum deviation. So that's why in the southeasterly heading, the deviation is reduced now, but it is still easterly. When the ship goes on southerly heading, even though the blue pole is closer to the blue end of the compass needle and the red pole is closer to the red end of the compass needle, they are still not able to generate any deviation. The red and red poles are repelling, blue and blue poles are repelling, but the strength of the poles of the ship is much weaker as compared to the strength of the Earth's poles. So that is why they are not able to turn the compass needle by 180 degrees. If the ship's field was more powerful, it would turn the compass needle by 180 degrees and the needle will start pointing south. But since these poles are much weaker, the magnetism of the ship is much weaker as compared to the magnetism of the Earth, they are not able to generate any deviation at all. When the ship goes on southwesterly heading, you can now see that the blue pole at the bow repels the blue end of the compass needle. Similarly, the red pole at the stern of the ship repels the red end of the compass needle, generating a westerly deviation. When the ship is heading in the westerly direction, this westerly deviation becomes maximum because the poles of the ship are at right angles to the poles of the Earth. The blue pole to the west of the compass needle attracts the red end towards it, generating a westerly deviation. Similarly, the red pole of the ship at the stern attracts the blue end of the compass needle, generating a westerly deviation. So maximum westerly deviation is generated on westerly heading. With the ship going on northwesterly heading, the deviation is still westerly, but the magnitude is reduced because the ship's poles are now coming in line with the magnetic poles of the Earth. Coming back to north, the deviation becomes 0. So you see from 000 to 180, the deviation was easterly, and from 180 to 360, the deviation was westerly. This is what we mean by a semicircular deviation. For one semicircular, the deviation has a single name. For another semicircle, the deviation has a opposite name. So therefore, it is called as a semicircular deviation. Now, another important thing which you can see from this diagram is that these poles of the ship also affects the directive force at the compass location. What is this directive force? Directive force is the strength of the magnetic field at the compass location which makes it point towards the north direction. Now with the vessel heading on the northerly heading, you can see that the poles of the ship are matching with the poles of the Earth. The Earth's north pole is a blue pole and the ship structure also has a blue pole north of the compass. So this blue of the Earth and blue of the ship are adding up, increasing the magnetic field. Similarly, south of the compass, we have the red magnetic pole of the Earth and the ship's pole is also red. So Earth's red and ship's red, they also add up to the directive force. So in this particular heading, northerly heading, the directive force is increased to its maximum. When the ship goes on easterly heading, in the easterly heading, the red and blue poles of the ship are neither north of the compass nor south of the compass. They are exactly east-west of the compass. Being east-west of the compass, they do not have any effect on the directive force. So the directive force is unchanged at this particular location. Now with the ship heading in the southerly direction, you see now the poles of the ship are opposite to the poles of the Earth. South of the compass, we have the blue pole of the ship and the red pole of the Earth. North of the compass, we have the red pole of the ship and the blue pole of the Earth. So with the ship pole and the earth pole becoming opposite, the directive force is reduced. So there is a maximum reduction in the directive force with the ship heading in the southerly direction. Moving on to the correction of coefficient B. Coefficients are always corrected on the heading on which they produce maximum deviations. Now the first thing which the compass adjuster needs to know is on which heading should I correct coefficient B. So we should always remember coefficients are always corrected on the heading on which they produce maximum deviation. Now coefficient B produces maximum deviation on easterly or westerly heading. So that is where it is corrected. For the coefficient to cause maximum deviation, it should act perpendicular to the needle. You remember on easterly or westerly heading, the blue and red pole of the ship are at right angles to the magnetic field of the earth, or they are acting perpendicular to the compass needle, giving maximum deviation. Now basic principle which is followed in correcting the compass is to cure like with like. Now what do we mean by curing like with like? It means permanent magnetism deviation are cured or corrected by using permanent magnets. Induced deviations are corrected or cured using induced magnet. So permanent is corrected with permanent, induced is corrected with induced. So same thing is mentioned here. Permanent deviation is cured or corrected with permanent magnets. Induced deviation is corrected with induced magnetism. Permanent magnetic field is therefore corrected using fore and aft permanent magnets which are placed horizontally. Now these magnets are so placed as to produce a permanent magnetic field at the compass location exactly equal and opposite to that of the ship. Now how we do that? Let us try to understand using this diagram. In this diagram, we see the same ship which we discussed for deviation. This ship is having a blue bow and it is having a red stern. Now you see the binnacle, this is the binnacle and the compass is fitted at this particular location. Now these blue and red poles, why were they generated? Because this particular ship was constructed on a southerly heading and during its construction it acquired these permanent poles. Now because of this blue and red poles of the ship, a magnetic field is generated. You can follow the laser pointer. The laser pointer now is moving on the magnetic field generated by the permanent poles of the ship. You see the magnetic field lines come out of the red pole and they go back into the blue pole. That is how the magnetic field lines are acting at the compass location. So what we do to correct it? We use fore and aft permanent magnets. We place them in the binnacle just below the compass and we place them in such a way that their poles are opposite to the poles of the ship. So we had the blue pole at the bow. When we place these correctors, we place the blue pole towards the stern. You see, we have red pole of the corrector magnet towards the bow. So when you place these magnets in the binnacle, they generate a correcting field. Right now the laser pointer is on the correcting field and you can see that the direction of the correcting field is opposite to the direction of the deviating field. So when you place these corrector magnets in the binnacle in the fore and aft direction with their poles opposite to the poles of the ship. Forward of the ship had a blue pole. Forward of this corrector has a red pole. So with the poles opposite to the poles of the ship, they generate a opposite field, thus correcting the deviation caused because of permanent B. So go ahead with your doubts, beta. They are bar magnets of circular cross section. They are 8 inches long and they come in two thicknesses, either 3 by 8 inches or 3 by 16 inches diameter. So where more powerful magnets are required, we use the thicker ones, that is 3 by 8 inches, or where less powerful characters are required, we use 3 by 16 inches diameter magnets. The size is decided by the compass adjuster. Once the ship is constructed and it goes out for sea trials, the compass adjuster checks the magnetism of the ship and decides upon whether he wants a thicker character or a thin character magnet. Slots are provided in the binnacle below the compass and the magnets are placed two in a row side by side. So when we place these character magnets, they are always placed in pairs. So one of the magnets is slightly to the starboard of the compass, another magnet is to slightly port of the compass. They are always placed in pairs. Now why are they placed in pairs? The reason for that is exactly in the middle of the binnacle or exactly below the compass, you have a periscope which is going into the wheelhouse. It is with the help of the periscope that you are able to see the magnetic compass at the helmsman location from the bridge. So because of this periscope, we cannot have the character magnet exactly below the compass location. Exactly, beta. Diagram of a binnacle. Now you see this particular plate which is fitted here. This plate carries the athwartship magnet tray. This is for correction of coefficient. Binnacle. Now you see this particular plate which is fitted here. This plate carries the athwartship magnet tray. This is for correction of coefficient C. And you see this particular plate which is fitted here. Now this plate carries the fore and aft magnets. Fore and aft magnets correcting coefficient permanent B. So when you open this plate, you will have access to these magnets. Now you can see these magnets here. These are the magnets which are fore and aft magnets here. Fore and aft magnets. You see this is the pipe which is going down, the periscope pipe. Also you see a small bucket hanging with the chain. This is known as a healing error bucket. So this is how the corrector magnets are placed to correct coefficient B, permanent B. Okay, beta. So any doubts till now, beta? Let's now move on to the second part of coefficient B, that is induced B. Induced B is caused by horizontal fore and aft magnetic field at the compass due to the induced magnetism in the vertical soft iron forward or aft of the compass. So you see, again it is a horizontal. To the second part of coefficient B, that is induced B. Induced B is caused by horizontal fore and aft magnetic field at the compass due to the induced magnetism in the vertical soft iron forward or aft of the compass. So you see, again it is a horizontal fore and aft magnetic field, but it is generated because of induced magnetism in the vertical soft iron forward or aft of the compass. Let me show you how it is generated. The vertical soft iron which we have on ship could be the forward mast, it could be a crane, it could be the funnel, or it could be a aft mast or a crane aft of the compass. Let's now move on to the second part of coefficient B, that is induced B. Induced P is caused by horizontal fore and aft magnetic field at the compass due to the induced magnetism in the vertical soft iron forward or aft of the compass. So you see, again, it is a horizontal fore and aft magnetic field, but it is generated because of induced magnetism in the vertical soft iron forward or aft of the compass. Let me show you how it is generated. The vertical soft iron which we have on ship could be the forward mast, it could be a crane, it could be the funnel, or it could be a aft mast or a crane aft of the compass location. Now all these vertical structures will be induced by the magnetic field of the earth, by the vertical component, Z component of the earth. If this particular ship is in northern hemisphere, the lines of force go vertically downwards, so they will be entering from the top end of the VSI and leaving out from the bottom end of the VSI. So the top end where they are entering gets a blue polarity, and the bottom end where they are leaving out gets a red polarity. So you see all the top poles of the vertical structures are blue. The top pole of the funnel is blue, the top pole of the forward mast, aft mast, or the cranes is blue. The bottom poles of all these vertical structures are red poles. Now out of these two, what affects our compass is the pole which is closer to the compass, and in this case, the top of the poles, which are the blue poles, are almost in line with the magnetic compass, and they affect our compass. If the same vessel goes in the southern hemisphere, now in the southern hemisphere, the magnetic lines of force come out of the Earth's surface. So you see, with the same vertical structures, in the southern hemisphere, the polarity is going to change. The lines will now enter from the bottom of these vertical structures, giving it a blue polarity, and it will come out from the top of these vertical structures, giving it a red polarity. So these being induced magnets, their polarity changes when the vessel changes from northern hemisphere to southern hemisphere. So as we discussed just now, the compass is generally situated at level with the top poles of the masts and the funnel. The top poles therefore affect the compass more as compared to the bottom poles of these vertical soft iron structures. We are aware that the compass is affected by that pole of the magnet which is closer to it. So we can see that the compass is situated in line or at level with the top poles of these vertical soft iron structures. So the top poles affect the compass more, and the bottom poles, being far away, do not affect our compass. Second thing to note is that funnel is the largest vertical soft iron structure on board. We may have the masts, we may have the cranes, aft mast, but the amount of steel which is used in construction of the funnel is much more, as well as the size of the funnel is much more as compared to the size of masts or cranes. So therefore funnel affects our compass most predominantly among all the vertical soft iron structure. So the effect of the funnel being the most predominant is considered mainly for induced B. So, compass needle, and the compass needle turns anti-clockwise or a westerly deviation is generated. When the ship goes to easterly heading, on a easterly heading, the blue pole of the funnel is at right angles to the field of the earth. It is exactly west of the compass. It is right angles to the field of the earth, and it provides or generates the maximum deviation. This blue pole of the funnel attracts the red end of our compass magnet and repels the blue end of our compass magnet, generating maximum westerly deviation. When the ship goes on southeasterly heading, in a southeasterly heading, the funnel blue pole is to the northwest of our compass, and again the blue end or blue pole of the funnel attracts the red end of our compass needle, and a westerly deviation is generated. But the westerly deviation now starts to reduce. Why the westerly deviation reduces is because the blue pole, which is generating this deviation, is now no more at right angles to the field of the earth, and it has started coming in line with the earth's magnetic field. Any pole, when it generates deviation, it generates maximum deviation when it is at right angles to the field of the earth. So when it is at right angles to earth's magnetic field, it will generate maximum deviation. And when it is aligned with the earth's magnetic field is running north-south. So when a pole comes north or south of the compass needle, it does not generate any deviation at all. So when the ship goes on southerly heading, the blue pole of the funnel comes exactly north of our compass, north of the compass needle. And since it is aligned with the magnetic field of the earth now, it does not generate any deviation at all. Will repel each other, and unlike poles will attract each other, right? Okay. Blue attracts the red pole of our compass magnet, the compass needle, and it generates a easterly deviation now. So easterly deviation is generated. When the ship moves on 270 heading, ship is heading west, then the blue pole of the funnel is now exactly east of our compass needle. So at this location, it is at right angles to the Earth's field. It attracts the red end of our compass needle and repels the blue end of our compass needle. The compass needle turns clockwise and generating a easterly deviation. At this point, the easterly deviation is maximum. What is the reason for that? Because the pole which is generating the deviation is at right angles to the magnetic field of the Earth. When the ship goes on northwesterly heading, this blue pole has come southeast of the compass needle, and it now repels the blue end of our compass needle, generating a easterly deviation. But the amount or magnitude of the deviation is reduced now because the pole is no more at right angles to the Earth's field, and it has started coming in line with the field of the Earth. So we can see that the deviation which is generated is semicircular from 000 to 180. The deviation generated is westerly. A westerly deviation is generated, and from 180 to 360, a easterly deviation is generated. Maximum deviation is generated on easterly and westerly courses, and zero deviation is generated on northerly and southerly courses. So you can see it is proportional to sine of the compass course. Sine 90 or sine 270 has a magnitude of 1, and sine 0 and sine 180 are 0. So it is proportional to the sine of the compass course. Now, how does this IB affects the directive force? You see, with the ship heading in the northerly direction, this blue pole of the funnel is opposite to or is opposing the south pole, which is of red polarity. The south pole of the earth is of red polarity. The pole on the funnel is blue polarity. So with these poles having opposite polarity, it reduces the directive force. When the ship is heading south, then the blue pole of the funnel and the blue pole of the earth, they match, increasing the directive force at the compass location. So whenever the ship is on a northerly component heading, northeast, north or northwest, the directive force is reduced because this funnel's blue pole is southward of the compass, giving or reducing the directive force. Whereas when the ship is on a southerly component heading southeast, south or southwest, the directive force is increased because the blue pole of the funnel is north of the compass needle. So beta, have a good look now and procedure, the concept behind the correction of induced B. We use like cures like principle. That means permanent deviation is corrected using a permanent magnet. Induced deviation is corrected using a induced magnet. Now, since this induced P is generated because of magnetism in the vertical soft iron, we will use the soft iron for correction of IP. So vertical soft iron is used for correction and it is used in the form of Flinders bar. The value of induced magnetism depends upon the length of the soft iron. Hence, the length of the Flinders bar is varied as per the correction required. Now, when we are doing a correction with permanent magnets, we can easily control the magnitude of correction by increasing or decreasing the number of magnets used. But what to do in case of a soft iron or in case of induced magnetism? The magnetism which will be induced is not in our control. It is dependent upon the magnetic field of the earth. So how can it be controlled or magnitude changed? Now that can be done by changing the length of the soft iron which is used as a corrector. The longer the soft iron, the more induced magnetism it is going to attain or have. So if we require a greater correction, then we use a longer Flinders bar, and in case the correction required is minute, then we can shorten the length of the Flinders bar as per our requirement. Now going more into analyzing the Flinders bar. The Flinders bar is placed inside a brass case. It could be a brass case or it could be a plastic or it could be any material which is non-magnetic. Now all the items which are used close to the magnetic compass in the binnacle, even the nails and screws which are used, they are made up of non-magnetic material. Only the correctors which we are using, they are either the permanent magnets or they are the soft iron rods or soft iron structures. Other than that, all the other parts of the binnacle are made up of non-magnetic material. So Flinders bar is placed inside a brass case or a non-magnetic case, and its length is 610 millimeters. And this casing is attached to the binnacle. The soft iron bars which are put into this casing are provided in pieces. It is not that they provide us with a single length Flinders bar which is 610 millimeters long. What is provided is they break up the 610 millimeters into small portions or small parts so that the compass adjuster can use the required parts or the required length of the Flinders bar. So I'll explain to you how this is used. Now the Flinders bar which is provided is in pieces. The first piece is 305 millimeters. Then the next piece is 152 millimeters. Then we have a piece of 76 millimeters, 38 millimeters, and then there are two pieces of 19 millimeters, making a total of 610 millimeters. Now, why are these provided in small pieces? Because as we just now saw, to vary the magnitude of correction, we can change the length of the flinder bar. So once these pieces are provided to us, we can use whatever pieces we require, and the other pieces can be kept as spare. So this is the approach behind providing the pieces. Now, how are these pieces utilized? When a flinder bar is supplied on the ship, along with these soft iron bars of these dimensions, a complete set of wooden pieces of the same dimensions are also provided. So you will have wooden pieces of all these dimensions along with the soft iron bars also provided. Now this is given to help us vary the length of the soft iron as per our requirement. Now on a ship which has a very big funnel, huge funnel, let us say we have a VLCC and it has got a huge funnel. Now if the funnel is quite big, that tells us that the induced P on that particular ship is going to be substantial. So we may require a flinder bar close to maybe 500 or 600 mm. Now on another vessel which has a very small engine and has a very small funnel, the correction required may not be very much. So we may require just about, let us say, 100 or 200 millimeters of the flinder bar. So these wooden pieces help us to vary the dimension or length of the flinder bar. Now let's move on to our next coefficient, which is coefficient C. Coefficient C is the maximum value of the semicircular deviation, which varies as the cosine of the compass course. It is caused by the horizontal authorship component of the ship's magnetic field. Now, if you look at the definition carefully, you will understand and realize that this definition is very much similar to coefficient B. In fact, coefficient C is almost having the same properties as we discussed in coefficient B, with only one difference. Bravo and Charlie, both these coefficients are exactly similar with only one difference. Coefficient C is dependent upon or is related to the authorship component of the ship's magnetic field. The last coefficient which we discussed, that is coefficient B, it was dependent upon the fore and aft component of the ship's magnetic field. And coefficient C is dependent upon the authorship component of the ship's magnetic field. Exactly like coefficient B, which had two components, the coefficient C also has two components. Coefficient C comprises of permanent C as well as induced C. So is it clear up to here, beta? Moving on to permanent C. Permanent C is caused by the Q component of the ship's permanent magnetism. We have three components of the ship's permanent magnetism, that is P, Q and R. P component lies in the fore and aft direction, Q component lies in the authorship direction, and R component lies in the vertical direction or orientation. So this is caused by the Q component, that is the authorship component of the ship's permanent magnetism. Now, to understand it more clearly, let's assume that we have a ship which is built in a yard on a easterly heading. Now, if the ship is built on a easterly heading, the magnetic lines of force will be entering into the ship's hull from the starboard side. So because of that, the starboard side will acquire blue polarity and the magnetic lines of force will be leaving out or coming out of the port side of the ship. So it will acquire a permanent red pole on the port side and a permanent blue pole on the starboard side. If a ship is built on a westerly heading, For a vessel built on a westerly heading, it will have the poles in the opposite direction. That means you will have a blue pole on the port side of the ship where the lines of force will be entering, and you will have a red pole on the starboard side of the ship where the magnetic lines of force will be coming out. You can see the deviation is proportional to coefficient C multiplied by cos of the compass course. So is this part clear, beta?
Yes, sir.
Yes.
Okay. C cos course. Let's now try to understand the deviation caused by coefficient C, that is permanent C. Now we are considering a ship which is built on an easterly heading. Just now we saw that a ship which is built on a easterly heading will have a blue pole on the starboard side and it will have a red pole on the port side. So you can see this ship in the diagram on different headings, cardinal and intercardinal headings, and the starboard side of the ship has a blue polarity and the port side of the ship has a red polarity. You see the compass needle fitted on the ship. The north end of the compass needle, which points towards the north, is of red polarity. So you can see the red end pointing towards north, and the end of the compass needle towards the south direction has a blue polarity. So you can see the blue polarity end pointing towards south. So let's try to analyze the deviation caused by this outward ship magnetism, that is permanent C, on different headings. Let us first consider the deviation caused on the northerly heading. So ship is heading north. You can see this topmost diagram shows the vessel heading in the northerly direction. Now when the ship is heading in the northerly direction, you can see that the blue pole of the ship, which is on the starboard side of the ship, is east of the compass needle. Now this blue pole of the ship is going to attract the red end of the compass needle, and the compass needle is going to swing clockwise. Looking from top, the compass needle is going to swing clockwise, which is easterly deviation. Likewise, on the port side, you see, on the port side, we have the blue polarity of the ship's magnetism. Sorry, the red polarity of the ship's magnetism. We have the red end. And this red pole of the ship's permanent magnetism is going to repel the red end of the magnetic needle, and again it adds on to, or it complements, the clockwise swinging of the compass needle looking from top. So we have a easterly deviation here. The red end on the port side repels the red end or the north end of the magnetic needle, and at the same time it attracts the south end or the blue end of the magnetic needle, resulting in the compass needle swinging clockwise looking from top, generating easterly deviation. And another important thing to note here is that these red and blue pole of the ship on the sides of the ship are at right angles to the compass needle, or you can say they are at right angles to the direction of the Earth's magnetic field. And when these poles, the ship's poles, are at right angles to the magnetic field of the Earth, they generate maximum deviation. So maximum easterly deviation is generated when the ship is on a northerly heading, 0, 0, 0 heading. Now let's take the ship on the easterly heading. Let us assume that the vessel is now heading 090. So on the easterly heading, you see in this part of the diagram, the blue and red poles which were present on the sides of the ship. The blue pole is on the starboard side and the red pole is on the port side of the ship. These poles are now exactly in line with the magnetic compass needle. The red pole is north of the compass needle and the blue pole is exactly south of the compass needle. Now, since these poles are exactly in line with the magnetic field of the Earth, they will not be able to generate any deviation at all. Deviation can only be generated when the poles are at some angle to the Earth's magnetic field or at some angle to the compass needle. So in this case, no deviation is generated. So that's why you see it is mentioned here, no deviation. Now you can see there is a red pole on the ship's port side, which is exactly north of the compass needle. The north end of the compass needle is also red. So if this was the only thing affecting the magnetic needle, that is these red and blue pole of the ship, this red pole will try to repel the compass needle, and it will try that the compass needle should point exactly southwards, because the red will be repelling the red end of the compass needle and it will be attracting the blue end of the compass needle. Likewise, you see the starboard end of the ship, which has a blue polarity, will try to repel the blue end of the compass needle, and it will also try to make the compass needle swing by 180 degrees pointing due south. But that does not happen. That does not happen because the ship's poles are much weaker as compared to the poles of the Earth. The magnetic poles of the Earth are much stronger as compared to the ship's magnetic field. Thus, these ship's magnetic poles are not able to generate any deviation at all. Attention to the ship heading in the westerly direction. Now in the westerly direction, you see the situation is more or less the same. The poles are exactly north or south of the compass needle. The only difference in this case is that the blue pole is north of the compass needle now, and the red pole is south of the compass needle now. In this condition also, with the ship heading in the westerly direction, no deviation is generated because the ship's poles are exactly in line with the magnetic field of the Earth, or they are exactly in line with the compass needle. When the poles are in line with the magnetic field of the Earth or the compass needle, they are not able to generate any deviation at all. So on the westerly heading, no deviation is generated. Now let's go to ship on the southerly heading. We have the ship on the southerly heading here in this part of the diagram. Now when the ship is heading south, you can see that these red and blue poles of the ship are now at right angles to the compass needle, or at right angles to the magnetic field of the Earth. So when these are at right angles, they will generate maximum deviation. So what type of deviation will be generated here? You see the starboard end of the ship, or the starboard side of the ship, has a blue polarity. This blue is going to attract the red end of the compass needle towards it. So the north end of the compass needle is attracted towards the port side of the ship, and the south end of the compass needle, which also has a blue polarity, is repelled away from this blue pole of the ship. Thus, the compass needle now swings anti-clockwise, generating a westerly deviation. Likewise, the red pole, which is there on port side of the ship, repels the red pole, or the north pointing pole of the compass needle, and attracts the blue pole of the compass needle. So thus adding on to this anti-clockwise swing of the compass needle, or adding on to the westerly deviation generated. So you can see when the ship is on southerly heading, westerly deviation is generated, and since the poles are at right angles to the compass needle, this deviation generated is the maximum deviation. Now let's take one intercardinal heading also. If you take the ship on a northeasterly heading, you can see on the northeasterly heading, the port side of the ship having a red polarity is now northwest of the compass needle, and it will repel the red end of the compass needle, generating a easterly deviation. Likewise, the blue end on the starboard side of the ship repels the blue end of the compass needle. This is southeast of the compass needle now, again generating a easterly deviation. So again a easterly deviation is generated, but this easterly deviation is lesser than what it was on the northerly heading, because on the northerly heading the ship's poles were at right angles to the compass needle, whereas on northeasterly heading The ship's poles are not at right angles, they are at a 45-degree angle now to the compass needle. So you can see this happening on the other intercardinal directions also. So what we observe here is that maximum easterly deviation is generated on the ship heading north. When the ship is heading northeast, this easterly deviation reduces. With the ship heading in the east direction, the deviation is zero, nil deviation. When the ship heads in the southeast direction, now a westerly deviation is generated. The deviation has changed its name now. When the ship is heading in the southerly direction, maximum westerly deviation is generated. With the ship heading in the southwest direction, again you have a westerly deviation. With the ship heading in the westerly direction 270, you have no deviation at all. And with the ship heading on the northwest heading, the needle or the compass has a easterly deviation. So you can see from 270 going up to 090 for this semicircle, the deviation is easterly, and from 090 onwards going up to 270 in this semicircle, the deviation is westerly. So this tells us this is a semicircular deviation, and it also tells us that the deviation is proportional to cos of the compass course. Cos of 0 and cos of 180 is of maximum magnitude, that's why you see maximum deviation here. Cos of 90 and cos of 270 has 0 magnitude, that's why you see 0 deviation on both these headings. The result of these magnetic fields or the magnetism of the ship on the directive force. Let's now see the correction of this particular coefficient. Now some important points which we are aware of is the coefficients are always corrected on the heading on which they produce maximum deviation. For the coefficients to produce or generate maximum deviation, it should be acting perpendicular to the compass needle or to the magnetic field of the earth. Now in our case, you can see the maximum deviation is being generated on northerly heading and on the southerly heading. It is on north and south heading that the poles of the ship are at right angles to the magnetic compass. So this coefficient would be corrected on a northerly heading or on a southerly heading. Basic principle which is followed in correcting a compass is to cure like with like. That is, a permanent deviation is cured with permanent magnetism, and induced deviation is cured with induced magnets. So in our case, this is being generated because of permanent magnetism of the ship. So we will be using a permanent magnet to correct coefficient permanent C or PC. So as we just now saw, cure like with like principle is used in the correction. PC, which is caused by ship's athwartship horizontal permanent magnetic field, is therefore corrected using athwartship permanent magnets placed horizontally. They are so placed as to produce a permanent magnetic field at the compass location which is exactly equal and opposite to that of the ship. Now in the diagram you see this ship. We are looking at the ship from the stern. You see we have a blue pole on the starboard end of the ship and we have a red pole on the port end of the ship. This was generating coefficient permanent C. Now on top you see this represents the binnacle of the magnetic compass, and in the binnacle we keep the corrector magnet. This small magnet on top is the corrector magnet which is placed. The holes are made in the binnacle in the athwartship direction, and these magnets are placed in those holes, making sure that the ends of the corrector magnet are opposite to the ends of the ship's permanent magnetism in the athwartship direction. The magnets which are used for correction are exactly similar to the ones which were used for correcting permanent B. So these outward shape magnets are bar magnets of circular cross section, which are 8 inches long and having 3 by 8 inch or 3 by 16 inch diameters. Two thicknesses are usually provided by the compass makers. In case a powerful magnet is required, then we will be using the 3 by 8 inch configuration, and in case we need a not very powerful magnet, a 3 by 16 inch diameter magnet can be used. Slots are provided in the binnacle below the compass, and the magnets are placed 2 in a row side by side. This is exactly as we corrected the permanent B. Only difference was in permanent B, the magnets were placed in the fore and aft direction. In correcting permanent C, the magnets are placed in the outward ship direction. To the second component of coefficient C, coefficient Charlie, which is induced C, in short known as IC. IC or induced C is caused by a horizontal outward ship magnetic field due to the induced magnetism in the vertical soft iron to port or to starboard of the compass location. So you see in this case very similar to coefficient IB. IB was caused because of a vertical structure which is forward or aft of the compass, and IC is caused because of a vertical structure which is port or starboard of the compass. Practically, IC does not exist on a merchant vessel, as the vertical soft iron to port and starboard of the ship's center line, if it is there, is symmetrically placed. So practically you see coefficient induced C or IC is not present on most of the merchant vessels because number one, there is hardly any prominent vertical soft iron structure to port or to the starboard of the compass location. Forward or aft of the compass, we have substantial VSI, big VSI structures. It could be the mast, it could be a crane or a derrick kind of structure. But port and starboard of the compass location, we usually do not have a prominent vertical soft iron structure. So if that structure is not there, coefficient IC or induced C will not be generated. This coefficient induced C or IC may be present on special type of ships where compass is placed off the center line. For example, in ships like aircraft carriers, you see in the aircraft carriers, to provide space for the runway, the bridge is off-centered to starboard or to port, and because of this, the compass location is also not on the center line, but it is offset to either port or starboard. Now in such a case, you can see in the diagram, the compass is placed off-center and the ship's fore and aft centerline bulkhead acts as a vertical structure in this case, and the induced magnetism generated by this vertical soft iron to port or starboard of the compass does generate induced C. Let's now discuss the deviation generated because of coefficient IC induced C. We have assumed a ship which is having a vertical structure to starboard of the compass location. So you can see here we have a vertical structure to starboard of the compass location, and this is a soft iron structure, and we are assuming that the ship is somewhere in the northern hemisphere. Now we know that in the northern hemisphere the magnetic lines of force, they re-enter into the Earth's surface. So these magnetic lines of force will be entering from top of the vertical structure and will be going out from the bottom of the vertical structure. Now since the top of the vertical structure is close to the compass location, this is what affects our magnetic compass. And in this case, with the ship being in the northern hemisphere, magnetic lines of force entering from top of the vertical structure, they give a blue polarity to the top of VSI, and that is why you see in the diagram we have a single blue pole to the starboard of the compass. You can see the ship in any of the cardinal and intercardinal heading. The ship is shown here on 4 cardinal and 4 intercardinal headings, and in all these diagrams you will see a blue pole getting generated to starboard of the compass because of this vertical soft iron. If the same ship happens to go into the southern hemisphere, the polarity will change to a red pole. So that is how induced magnetism works. So let's now try to see the kind of deviation which this vertical soft iron structure generates. So let's assume the ship on a northerly heading first. Now with the ship on a northerly heading, you can see the compass needle represented by the red and blue poles arrow shown in the diagram. So this represents our compass needle, and we have a blue pole to the starboard of the compass needle, or to the east of the compass needle in this case. This blue pole attracts the red end or the north end of our magnetic compass needle, and at the same time this blue pole repels the blue end or the south end of our magnetic needle, thus generating easterly deviation. Now the deviation generated at this location is maximum. A reason for deviation being maximum is that this blue pole is at right angles to the compass needle, or it is at right angles to the Earth's magnetic field line. Whenever the disturbing pole, the blue pole or the red pole, is at right angles to the Earth's field or to the magnetic compass, it generates maximum deviation. So we have maximum easterly deviation when the ship is on a north heading. Now, since the pole is neither to the north of the compass nor to the south of the compass, it has no effect in the directive force. The directive force can be affected by this pole if it is north of the compass or south of the compass. But in this case, it is perfectly aligned to the east of the compass location, thus making no change in the directive force. Now, let's assume the ship on a easterly heading. So with the vessel on a easterly heading, this blue pole now comes exactly south of the compass needle. The blue pole is exactly south of the compass needle. Now this blue pole would try to repel the blue end of our compass needle. It is close to the blue end of our compass needle. It will try to repel it. And if this was the only force affecting our compass, the compass would have pointed towards south, because this blue pole will try to attract the red pole of the compass. But that is not the case. This pole is not able to generate any deviation at all, because the Earth's magnetic field, which is much more powerful as compared to this blue pole, keeps the compass pointing in the northerly direction. And the blue pole is not able to generate any kind of deviation. For generating deviation, the blue pole has to be at some angle to the magnetic lines of force. It has to be either east or west of the compass needle. So in this case, it is exactly aligned with the compass needle and as well as the magnetic lines of force, thus generating no deviation at all. So beta, will you be able to understand the other ones? It is exactly the same as we did in IB. So shall I explain the other headings, or can we move ahead?
We can move ahead. No.
Coefficients are always corrected on the heading on which they produce maximum deviation. In this case, maximum deviation is generated on northerly or southerly heading, so the correction is made on one of these two headings. For the coefficient to cause maximum deviation, it should act perpendicular to the needle. So we have seen in the previous diagram that on northerly and southerly heading, the pole is at right angles to the compass needle, thus generating maximum deviation. Basic principle which is followed in correcting the compass is to cure like with like. That is, permanent deviation is cured with permanent magnets and induced deviation is cured with a induced magnet. So this being a induced magnetism will be corrected using a induced magnet only. A normal merchant vessel does not have IC, therefore no correction is generally required. However, if the compass is badly placed, IC will be present. Now this is corrected using the same principle as induced P. Thus, a flinder bar can be placed port or starboard of the compass, opposite to the side on which the outward shipped vertical soft iron is predominant. Exactly the same thing was done in induced P also. We placed a flinder bar opposite to the funnel. So likewise in this case also we place a flinder bar which is opposite to the VSI structure to port or starboard of the compass location. Now one important stand here is that if a merchant vessel has both the coefficient IB as well as IC together, we have a method with which both these coefficients can be corrected in one go. Instead of using two flinder bars, the correction can be done using only a single flinder bar, which will correct both these coefficients together, induced P as well as induced C. So how is this done? Let's see. A merchant vessel will definitely have induced P because of the funnel, the mast, vertical structure fore and aft of the compass will certainly be present, and it is corrected using a flinder bar forward or aft of the compass as required. If induced C is also present, then another flinder bar will be required to port or starboard of the compass opposite to the VSI. It is very much convenient to use only a single flinder bar and slew it. Slew basically means turning it from the fore and aft line to port or starboard of the compass. So the fundamental of this correction is that we take a single flinder bar. Instead of placing it forward of the compass, we slew it or we turn it in a direction which is opposite to the resultant of IB as well as IC. So once it is placed in that way, this is able to correct, this flinder bar, single flinder bar is able to correct both these coefficients together. Now,
sir,
which arises in our mind is, how do we determine the angle by which the flinder bar should be slewed? This is also called as the slew angle. And also direction in which the flinder bar should be slewed, to clockwise or to anti-clockwise. These are the two things which we need to know before we correct a IB and IC combination using a single flinder bar. Now for this, let us understand it using one example. Let's assume that in the diagram, you can see the laser pointer. In the diagram, this is the compass location where the laser pointer is right now. Now we have a funnel which is aft of the compass needle. The ship is right now, let's assume the ship is heading north 000. So we have the flinder bar at this particular location. So this flinder bar is generating IB or induced P component. So this vector represents the IB component. Now let's also assume that on this particular ship there is a vertical soft iron structure to starboard of the compass, and that structure is present here at this particular location. Now this structure is going to cause induced C, and this vector where the laser pointer is right now, this vector represents the component or coefficient IC. Now, if we take a resultant of these two coefficients, the resultant can be easily obtained by making a parallelogram. So if you make a parallelogram using these two IB and IC vectors, the diagonal of the parallelogram, this diagonal of the parallelogram gives us the resultant of these two forces. Now we can find out the magnitude of this resultant by using the Pythagoras theorem. It will be equal to the base square plus the perpendicular square under root. That is IC square plus IB square under root will give us the magnitude of this effect, which is the resultant effect of IB and IC. Also, we can easily find out this angle. This is the angle between the 4.5 line. This is the 4.5 line and the resultant of IB and IC. In the diagram, we have represented it by capital M, and this particular angle, capital M, basically gives us our slew angle. We can easily find out this angle M. Now we know tangent theta is equal to perpendicular upon base. So tangent of this angle M will be equal to the perpendicular. You can see the perpendicular is basically the IC component, and the base is the IB component. So you see tangent of this angle will be equal to IC upon IB. So you can see the formula here. Tangent of the slew angle is equal to IC upon IB. So if we know the magnitude of IB and we know the magnitude of IC, then we can easily calculate the slew angle. The slew angle, once calculated, gives us the information how much turning or slew is required for the flunder bar. Now the flunder bar has to be placed in a direction which is opposite to the resultant of these two forces. So opposite to the resultant, we place the flunder bar somewhere here in this direction. The magnitude of the flunder bar or the length of the flunder bar is decided by the magnitude of the resultant, and the slew angle is this angle M, which we have calculated using the formula tan of slew angle is equal to IC upon IB. So is it clear, beta? Now when we make the combined correction for IC and IB, we have to also find out what is the heading on which the ship should be when the correction is made. Now coefficients are always corrected on a heading on which they produce maximum deviation. For the resultant of IC and IB to cause maximum deviation, it should act perpendicular to the needle. The compass needle always lies in the north-south direction. So for the force to act perpendicular to this direction, this resultant vector should be acting in the easterly direction. If this resultant vector is in the easterly direction, it will be acting at right angles to the compass needle, generating maximum deviation. Now for this resultant to lie in the easterly direction, it has to swing by an angle, or the vessel has to swing by an angle equal to 90 minus m. You can see the laser pointer. This is the angle by which the vessel has to be swung to the port side so that the resultant is acting in the easterly direction, which is perpendicular to the compass needle heading north and south, or aligned in the north and south direction, generating maximum deviation. So swing the ship 90 minus m degrees to port for the combined correction. Now another option which is available to us is if this resultant vector acts in the westerly direction. If it acts in the westerly direction, even then it will be acting at right angles to the compass needle, and this will happen when the ship is on a reciprocal heading to the initial one. If you swing the ship 90 minus m to port, we obtain one of the headings, and also on a heading reciprocal to that, 180 degrees apart from that, you will see that this is the second option available to us to correct IB and IC together. Coefficient now is coefficient D, coefficient delta. Coefficient D is the maximum value of quadrantal deviation. Now this is the first difference which you see in this particular deviation. It is a quadrantal deviation. Coefficient Bravo and Charlie, which we saw, were semicircular deviation. This one is a quadrantal deviation, meaning every quadrant or every 90 degrees it changes its sign from east to west or west to east, and it varies proportional to sine of twice the compass course or sine of 2 into compass course. It is caused by a horizontal field due to induced magnetism in horizontal soft iron situated symmetrically about a 4.5 line through the compass. Now this coefficient is entirely generated by induced magnetism. There is no contribution of permanent magnetism in this coefficient. It is generated only by induced magnetism. We have seen induced magnetism was responsible for coefficient A also, but in that case, it was not symmetrical soft iron. It was unsymmetrical soft iron. If it was present forward of the compass, it was not present aft. If it was present on port side of the compass, it was absent on the starboard side. Whereas in this coefficient, you see it is situated symmetrically about a 4.5 line through the compass. The induced magnetism also resulted in IB and IC, but in both these cases, we had the vertical soft iron, forward or aft or port or starboard of the compass. In this case, it is not the vertical soft iron, but the horizontal soft iron which generates coefficient delta. Beta, let's take a short break, 5 minutes. There is an important call coming in. So let's meet after 5 minutes. Say 45? Okay, beta. Coefficient now is coefficient D, coefficient delta. Coefficient D is the maximum value of quadrantal deviation. This we had covered last slide. Now let's go into the generation or the cause of the coefficient D. Generally, HSI, horizontal soft iron structure on merchant ships are transverse beams and fore and aft longitudinals or girders. Now out of these two, the transverse beams are much more in number. They are present in the length profile of the ship, which is much more as compared to the breadth profile of the ship. The fore and aft longitudinal are present in the breadth profile. So transverse beams are much more in number as compared to the longitudinals. And also the ends of the transverse beams are much closer to the compass, making their effect much more predominant. Now the first thing to appreciate here is that if we have a transverse beam and if we have a fore and aft longitudinal exactly similarly placed about a compass having the same size, then they are going to cancel out the effect of each other. If they are perfectly balanced, equal to each other, they are going to cancel out each other. Now that is not the case. The transverse beams are much more in number, and secondly their ends are closer to the compass location. The ends of the fore and aft longitudinal are close to the bow and stern of the ship, which are far away from the compass location, whereas the beams stretch over the entire length of the ship and the ends of the beam are closer to the compass location as compared to the longitudinals. So number one, the beams are much more in number, and number two, their ends are closer. So thus making the effect of the athwartship beam or transverse beam much more predominant as compared to a fore and aft longitudinal. So in our example, when we understand the deviation generated by coefficient D, we will be assuming one athwartship beam, a horizontal soft iron, and getting or understanding the deviation from there. Let's start deviation diagram for coefficient D. So we have a ship here and in this ship we have represented one outward ship beam. As we just discussed that their effect is much more predominant as compared to the longitudinal. So we are assuming a outward ship beam here on the ship. We have the compass needle. So you can see the red end of the compass needle pointing towards north and the blue end of the compass needle pointing towards the south direction. So let's now first concentrate on the northerly heading. The vessel is on a northerly heading in this diagram. Now when the ship is heading north, this outward ship beam is at right angles to the magnetic field lines of the earth. The magnetic field lines are running from south to north, and this beam is lying in the east-west direction, perpendicular to the earth's magnetic field. Now since it is perpendicular, there is no induction or almost zero induction which happens on the beam. If there is no induction, no poles are generated, and if there are no poles, no deviation is generated. So the deviation generated on northerly heading is 0. Let's now take the ship on a easterly heading. So in this part of the diagram, you see the vessel heading in a easterly direction. Now with the ship heading on a easterly direction, this outward ship beam is now perfectly aligned with the magnetic field of the earth. Since it is perfectly aligned, it will have the maximum induction caused because of the earth's magnetic field. The magnetic field lines will be entering from the south end or the starboard end of the beam, and they will be coming out from the north end or the port beam end of the outward ship beam. The magnetic lines of force entering from south generate a blue pole. So we have a blue pole south of the compass needle, and we have a red pole north of the compass needle. Now these blue and red poles are exactly south and north of the compass needle. Being exactly aligned with the compass needle, they are not able to generate any deviation at all. Generating a deviation, the pole has to be at some angle to the magnetic field line or to the compass needle. In this case, it is perfectly aligned. Even though the poles are most powerful in this case, they are still not able to generate any deviation because these are aligned with the compass needle. So the deviation generated is again nil. Zero deviation is generated. Now let's take the ship on a northeasterly heading. Now with the vessel on a northeasterly heading, you see the outward ship beam is partially aligned with the magnetic field of the earth. It is at a 45-degree angle to the earth's magnetic field. Now being partially aligned, the poles which are generated, they are partially powerful. They are not at their maximum power. They have partial power. But at the same time, these poles are at a 45-degree angle to the compass needle. Thus, they are able to generate a deviation here. The red pole which you see, which is on the port side of the ship, this red pole is towards the northwest of the compass needle, and this red pole repels the red pole of our compass needle, thus generating a easterly deviation. Likewise, if you pay your attention to the blue pole is southeast of the compass needle, and this blue pole repels the blue end of the compass needle, thus assisting in generating easterly deviation. So easterly deviation is generated in this case with the vessel heading in the northeasterly direction. Now this deviation which is generated here is the maximum easterly deviation. Why it is maximum? You can easily understand it. If the vessel changes its heading and moves toward the northerly heading, as it moves toward the northerly heading, you will see that the outward ship beam is lesser aligned with the magnetic field of the earth. It is slowly approaching a 90-degree angle to the earth's magnetic field line, and thus the power of these poles which are generated keeps on reducing. The outward ship beam angle to the magnetic field line keeps on increasing thus reducing the induction and the poles becoming weaker and weaker. Because of the poles becoming weaker, the deviation keeps on reducing. Now, if the vessel swings to the starboard side and tries to approach the easterly direction, the poles are becoming stronger, but these poles are now coming in line with the magnetic needle. Now, as they come in line with the magnetic needle, they are not able to generate that much deviation, and the deviation starts to decrease. So maximum deviation is caused on the northeasterly heading, and zero deviation is caused on northerly heading as well as easterly heading. Now you can appreciate here the deviation is proportional to sine of twice the compass course. When the heading is 0, 2 into 0 is 0 again, sine of 0 is 0, therefore 0 deviation. When the heading is 45 degrees, 2 into 45 is 90, sine of 90 is 1, which is the maximum value, generating maximum deviation here. And when the vessel is heading in the easterly direction, heading is 90, 2 into 90 is 180. Sine of 180 is again 0, thus giving us a 0 deviation. So two things which we realize here. One, the deviation is proportional to sine of twice the compass course. Second, the deviation is quadrantal. You see, over one quadrant, it was 0 on the northerly heading, became maximum easterly on the northeast heading, and became 0 again on the easterly heading. Going further, if the ship swings to a southeasterly direction, we will see here that the deviation which is generated is of opposite name now. We have a westerly deviation generated here. So you can see these four quadrants showing the deviation generated, and it tells us that this is a quadrantal deviation. Now the same principle can be applied to any of the other headings, and you can appreciate the deviation being generated proportional to sine of twice the compass course. Now another important thing here is that the directive force in this case is never increased on any heading. You can check all the headings. The directive force is not affected on some of the headings. Yeah, like you see on northerly heading, there is no effect on the directive force, whereas on northeasterly, easterly and southeasterly headings, the directive force is decreased. So why is this decreased? This is decreased because the blue end of the beam is aligned south of the compass needle, where we have the red end of the earth. Since the pole of the beam is opposite in direction or opposite in polarity to the pole of the earth, it reduces the directive force. Soft iron structures, because of induced magnetism, the correction is also done using a soft iron corrector. Since there is predominance of outwardship beams and also their ends are closer to the compass, these have much more effect than the fore and aft longitudinals. This effect is corrected by providing two soft iron spheres placed one on either side of the compass in the outwardship plane. This will become all the more clear with the help of a diagram. So we will discuss this correction using a diagram. As we just now discussed, the correction is done on any one of the intercardinal heading where the deviation caused due to coefficient D is maximum. In the unlikely event of a ship having more longitudinals than the outwardship beams, and the longitudinals becoming more powerful as compared to outwardship beams, the spheres will be placed fore and aft of the compass. Now, this could be very rare on some special type of ships where the structure of ship is such that the longitudinals are more in number as compared to the beams, and also their ends are closer to the compass. Let's now try to understand coefficient T correction offered by the soft iron spheres. So let's have the ship in our diagram. You see the ship heading on a northeasterly direction. So why is the ship heading in the northeasterly direction? That's because all the coefficients are corrected on the heading where they are the strongest. So we know coefficient D is the strongest on intercardinal headings. That's why we have chosen a intercardinal heading, and that is northeast. Let's now show the magnetic compass on our ship. You can see the compass coming up. The compass needle is visible on the screen now. The north end of the compass needle having red polarity and the south end of the compass needle having the blue polarity. Let's now show the outward ship beam. Now this is the soft iron structures, a outward ship beam, which is responsible for generating coefficient T, coefficient delta. Now since this beam is a soft iron structure, it does not have any permanent magnetism or any permanent poles. The magnetism in this beam is induced magnetism, and it is generated by the magnetic field of the earth. So let's now show the poles of the earth in our diagram. You can see the south pole of the earth coming up on the screen at the bottom, and it is having a red polarity. And we can now see the north pole of the earth, north magnetic pole of the earth, coming up at the top of the screen, having a blue polarity. Let's also show the magnetic lines of force in our diagram. We are aware that the magnetic lines of force, they come out of the red pole and they enter or they go towards the blue pole of the earth. So you can see the magnetic field lines shown by these arrows. The magnetic field lines are generating from the south pole of the earth, the red pole, and they are going into the magnetic north pole, the blue pole of the earth. Now these magnetic lines of force will be inducing the outward ship beam present on the ship. Now the starboard end of the beam is the point where these magnetic lines of force are entering, and we are aware that wherever the magnetic lines of force enter, they generate a blue polarity. So you can see a blue pole being generated at the starboard end of the soft iron outward ship beam. Now the port side end of the outward ship beam is the point where the lines of force are leaving or going out of the beam, and wherever the lines of force go out, they generate a red pole or a red polarity. So that's why you can see a red pole being generated at the port end of the outward ship beam. Now these red and blue poles generated at the end of the beam are the ones which are causing coefficient D, which are causing the deviation in our compass. The red pole on the port end of the beam is repelling the north end of our magnetic compass needle. Red and red, they repel each other, and the needle turns clockwise. Looking from top, the needle turns clockwise or in the easterly direction, generating a easterly deviation. Likewise, you see the blue pole which is generated on the starboard end of the outward ship beam repels the south end of our compass needle, both having blue polarity, blue repelling blue, and again complementing the easterly deviation. So the compass needle turns clockwise looking from top of the compass, and it generates a easterly deviation. Now for correcting this deviation, we use the principle of like cures like. So we correct it using a soft iron corrector. And in this case, we use soft iron spheres. So let's place the spheres. You can see the spheres now coming up on the sides of the compass in the outward ship direction. There is a sphere on the port side of the compass, and you have the second sphere on the starboard side of the compass. Now these are soft iron spheres, so they also do not have any permanent poles. these spheres will also be induced by the Earth's magnetic field lines. The end of the sphere where the magnetic field lines enter will get a blue polarity. So you see the south end of the sphere. Let's first concentrate on the starboard side character, starboard side sphere. You see the south end of the sphere right now where the laser pointer is the point where the magnetic lines of force are entering and thus generating a blue polarity in that direction. The top end or the north end of the sphere is the point where the magnetic field lines are leaving or going out from the sphere, thus generating a red polarity. Similarly, if you have a look at the port side sphere, the bottom end where the laser pointer is right now is the one where the magnetic lines of force are entering, giving it a blue polarity. And you can now see the points where the magnetic lines of force are leaving or coming out from the spheres, they are having red polarity. So we have the corrector spheres placed in the outward-shift direction of the compass to port and starboard of the compass. And we have these corrector spheres induced by the Earth's magnetic field. Points where the Earth's magnetic field lines are entering into the spheres have got blue polarity, and the points where the magnetic lines of force are coming out of these soft iron spheres have got a red polarity. Now let's first concentrate on the starboard corrector sphere. Now this starboard corrector sphere is having both the magnets, both the poles. You have the red pole as well as you have the blue pole. Now that pole of the corrector affects the magnetic compass, which is closer to the compass. Now out of this red and blue pole of the starboard corrector, the pole which is closer to the compass is the red pole. So from the starboard corrector, red pole is what is affecting the compass. And this red pole is going to attract the south end of the compass towards it, thus cancelling out the easterly deviation. When the red pole of the corrector magnet, the starboard corrector magnet, attracts the south end of the compass needle, south end has a blue polarity, opposite poles attract. So when it attracts the south end, the compass needle turns anti-clockwise, thus cancelling out the deviation generated. You can see the starboard end of the beam was having a blue polarity, whereas the starboard soft iron corrector having a red pole closer to the compass is cancelling the effect of the outward-shift beam. Now let's take our attention to the port side corrector. Now in the port side corrector, we are having both the poles, blue pole as well as the red pole, but the pole which is closer to the compass needle is the blue pole. The blue pole is closer to the compass needle, and this blue pole attracts the north red end of our magnetic compass needle. North end of the compass needle having a red polarity, corrector magnet pole closer to the compass having a blue polarity, blue and red being opposite poles attract each other. This also leads to the magnetic needle swinging anti-clockwise looking from top, thus cancelling out the deviation generated. You can also have a look at the end of the outward-shift beam. The end of the outward-shift beam was having a red polarity deviating our compass, and the corrector magnet pole closer to the compass has a blue polarity, which cancels out the effect of the outward-shift beam. So you can now see the corrector magnets, soft iron corrector magnets placed in the outward-shift direction, cancelling out the deviation generated because of the ends of the outward-shift beam.
Sir, instead of these pairs, can we use plates?
Brackets attached to the binnacle so that their centers are in the same plane as the plane of the compass. The magnitude of the correction can be varied by shifting the spheres closer or farther from the compass. So you can see the spheres placed in the outward ship direction. You can see this is the bracket which is fitted. You can see the channel also here. Likewise, on the port side, you have this sphere as well as the channel and the bracket. So on the right side diagram, you can see this is the bracket, the channel. There is a scale here on the channel which helps us to correctly position the spheres at equal distance from the compass. So these are the soft iron sphere correctors placed on the sides outward ship direction, port and starboard of the compass to correct coefficient delta. Now coming to the question that why we use a spherical shape for the soft iron corrector. The reason for using spherical shape is sphere is the most regular geometrical shape. You look at a sphere from any aspect or from any angle, from any direction, it presents the same face or the same aspect. So irrespective of the vessel heading in any direction, the vessel rolling or pitching, in any case whatsoever, the sphere present a uniform correction in all the conditions. So that is why the shape of the corrector which is chosen is spherical. So you can see a actual compass with a picture clicked right from top. You can see the spheres placed on either side, starboard side and the port side. You can have a look at the channel also here. You can see a slot provided. This is the sliding channel. There are nuts which are fitted below these spheres and they can be tightened in location using those nuts. You can also see the flinder bar which is forward of the compass location. So with this we complete coefficient to the next coefficient which is coefficient E, eco. Coefficient E is very similar to coefficient delta. Very similar to coefficient delta with only one difference. It has, you can assume it has a phase difference of 45 degrees. Coefficient delta was powerful or the strongest on intercardinal headings and it was 0 on cardinal headings. Whereas coefficient eco is 0 on intercardinal heading and it is maximum on the cardinal headings. So very similar. Coefficient T is the maximum value of quadrantal deviation. It is again a quadrantal deviation which changes its name every 90 degrees, which varies as the cos of twice the compass course. It is caused by a horizontal field at the compass position due to induced magnetism in the horizontal soft iron situated symmetrically about a 45-degree line through the compass position. So for generation of coefficient T, we need to have a soft iron structure on the ship in this particular orientation. You can see a soft iron structure at a 45-degree angle to the fore and aft line or to the outward ship line. So normal merchant vessel will not have any structure like these. The fore and aft longitudinal as well as the outward ship beams are generally the strength members of a normal merchant vessel. So we will not have a substantial structure, a soft iron structure at a 45-degree orientation. And this is exactly the reason why coefficient T is absent in a normal merchant vessel. Or if you have a soft iron structure in this particular orientation at a 45-degree angle, now this soft iron is divided at the compass location. So both these structures are usually absent on normal merchant vessels. Let's now see the deviation generated because of this structure. So let's first have a look with the ship on a northeasterly heading. When the vessel is on a northeasterly heading, this structure is perfectly aligned with the magnetic field line of the ship, thus generating very strong poles at both the ends of the soft iron structure. But these poles are exactly north and south of the compass location, thus generating no deviation at all. For generating any deviation, the poles generated should be at some angle to the north-south line, or at some angle to the magnetic field of the earth or to the magnetic needle, and in this case, this angle being 0, no deviation is generated. Now let's take the ship on a easterly heading. With the vessel on a easterly heading, we can see that this structure is now partially aligned with the magnetic field of the earth, partially aligned. So the poles generated are of the partial power, but these poles are at a 45-degree angle. This is where maximum deviation is generated by these poles. So on the easterly heading, you see maximum deviation is generated. In the previous case, with the vessel heading in the northeasterly direction, the deviation generated was 0. So on an intercardinal heading, the deviation generated is 0. On a cardinal heading, the deviation generated is maximum. Now let's take the ship on a southeasterly heading. When the ship goes on a southeasterly heading, you see this structure is now at right angles to the magnetic field of the earth. So being at right angles, the induction is 0, negligible, no poles are generated. With no poles being generated, the deviation generated is also 0, so nil deviation on southeasterly heading. So you see 0 deviation on the intercardinal heading and maximum deviation on the cardinal heading. If you look closely, this entire deviation diagram is very much similar to the diagram of coefficient delta, as if the coefficient delta diagram has been rotated by 45 degrees. So that's why I said there is a 45 degrees phase difference between delta and eco. So clear beta, is that clear? In case of coefficient E, the structure is at a 45-degree angle. So that's why the corrector are also placed at a 45-degree angle to the fore and aft line. So in this diagram, you can see this is the case we discussed in the deviation diagram. We have a structure in this particular way. The soft iron spheres are placed in the same orientation, thus cancelling out the effect of the soft iron structure. Now beta, the last important thing about coefficient is on a particular ship, coefficient D and coefficient E, delta and eco, both these coefficients are present together. When both coefficient delta and eco are present, they can be corrected by using a single set of spheres. We do not need to use two separate set of spheres. Coefficient delta is corrected by placing the spheres in the outward shift direction. Eco is corrected by placing the spheres at a 45-degree orientation to the fore and aft line. But if both of them are present, they can be corrected using a single set of spheres which are slewed or turned to some intermediate angle in the direction of the resultant of both these coefficients. Now, how do we decide what is the direction in which the spheres should be placed? If it was only delta, the placement was simple. They need to be placed in the outward shift direction. If it was only eco, the orientation was similar to the structure present on the ship. But if both are present, a single set of sphere can be placed and slewed. The slew angle is calculated by the formula tangent of twice the angle of slew is equal to coefficient eco divided by coefficient delta. So whatever is the magnitude of eco divided by the magnitude of coefficient delta gives us tangent of twice the angle of slew. So angle of slew can be obtained using this formula. Once the slew angle has been calculated, the spheres are initially placed to correct coefficient delta. For correcting coefficient delta, the spheres are placed in the outward shift direction. After correcting delta, the spheres are now slewed by that particular angle. Now, how do we decide whether the spheres are to be turned or slewed in the clockwise direction or the anti-clockwise direction? Practically on board, it is very simple. Once you have placed the spheres in the outward-shift direction, they should be slewed towards the direction of the structure, which is at a 45-degree angle to the fore and aft line. So in whichever orientation the 45-degree soft iron structure is present, the sphere should be slewed towards that structure. Theoretically, it can also be obtained, it can also be found if delta and echo are of the same sign, both are easterly or both are westerly, the spheres are slewed clockwise, and if they are of opposite signs, the spheres are slewed anti-clockwise looking from top. Now, after obtaining the slew angle, after obtaining the direction in which the spheres are to be slewed, the next question which the compass adjuster has to be clear about is, what is the heading on which the ship should be when this combined correction is being done? If it was only coefficient delta, we know the vessel has to be on any one of the intercardinal heading, that is where it is the strongest. If it was only coefficient echo, we know the vessel should be on some cardinal heading, that is where coefficient echo is strongest. But when we are having a combined correction of delta and echo, what should be the heading of the ship? Now for this, the maximum deviation due to delta and echo combined occurs when the spheres lie in the northeast or southwest direction of the compass location. Reason being that any horizontal soft iron will produce maximum deviation when they lie in the northeast southwest or northwest southeast of the compass location. And this using a diagram. Now beta, this example which I am showing you, this is one of the questions which come in our paper. So this is slightly tricky and complicated. So if you want to take a short 5 minutes break, we can take that and then we can go ahead with this. So now let's try to understand the combined correction of coefficient delta and echo, this concept using a actual question. On a ship, the soft iron spheres are observed to be placed in a relative direction 100 and 280 with respect to the ship's head. Analyze the cause for same and find the heading on which the sphere correction should be done. This is the actual question which has come in the past papers on this particular topic. So let's first try to understand what the scenario is. What does the question mean? Let me show you a diagram. So we see the ship here, and on the ship we have the compass. The circle which you see in the center represents the compass, and the spheres are fitted on this ship in a relative direction of 100 and 280. This is a relative direction with respect to the ship's head. Let's assume for the time being that the ship is heading north. So this is the north direction as well as the ship's head, and the spheres are lying in a direction 100. So from the ship's head going clockwise up to an angle of 100, this is where one of the sphere lies. And going further 100, 120, 130, 180, then 270 and 280. This is the direction in which the second sphere lies. So we are now able to see what is the orientation or location of the spheres with respect to the compass. So the first thing they are asking in the question is, analyze the cause for same. Now, one thing which becomes clear to us is that on a normal merchant vessel, the spheres are usually placed in the outward ship direction. That means in a relative 090270 direction. Now, that happens when the ship only has coefficient delta. If coefficient eco is present, the spheres will be placed either northwest southeast or northeast southwest of the compass. We are aware that when both the coefficients are present, that is delta and eco, that is the case when the spheres are slewed at a particular angle, and that is the situation here. So this clearly tells us that on this particular vessel, we have coefficient delta as well as coefficient eco. Both these coefficients are present on the ship. And that is the reason why the spheres are slewed. They are fitted at an angle, not in the outward ship direction, but at an angle. Another thing which we observe is, looking from top, the spheres are slewed in a clockwise direction. If you see, they are slewed by an angle of 10 degrees in a clockwise direction. Looking from top, the spheres are turned in a clockwise direction. So this gives us the second inference here, that coefficient delta and coefficient eco are of the same sign, because we are aware when delta and eco are of the same sign, the spheres are slewed clockwise. If delta and eco are of the opposite signs, the spheres are slewed anti-clockwise. So that is the second inference which we get. First inference, this ship has coefficient delta as well as eco. Second inference, coefficient delta and coefficient eco are having the same sign. Find the heading on which the sphere correction should be done on this particular ship. Now always remember the fundamental, that whenever we are doing any sphere correction, it may be coefficient delta, it may be coefficient eco, or it may be the combined correction for delta and eco. In all these cases, whenever we are doing any sphere correction, we have to ensure that the spheres are at a intercardinal direction from the compass location. That means the sphere should be either northeast of the compass, or southeast of the compass, or southwest of the compass, or northwest of the compass. Whenever the correction is being done, the heading of the ship should be such that the spheres are at a direction which is an intercardinal direction from the compass location. So for doing the combined correction also, we need to take the spheres to a intercardinal direction. Now let's assume we are trying to take the starboard corrector sphere to the southeasterly direction of the compass. Now if you want to take the starboard corrector sphere southeast of the compass, that basically means that the sphere has to be turned clockwise. The sphere has to be turned or slewed clockwise by an angle of 35 degrees. It is right now at an direction of 100, and we need to take it to a direction of southeast, which is 135. So we have to turn it clockwise by an angle of 35 degrees. Now that means the vessel has to swing to the starboard side. Turning clockwise, looking from top, means swinging to starboard. The vessel has to swing to the starboard side by an angle of 35 degrees. Now if the ship swings to starboard by an angle of 35 degrees, the heading on which the ship would be that time is 035 degrees. So the heading of the ship will be 035 degrees. When the ship is heading 035, the starboard corrector sphere is going to come exactly southeast of the compass. The port side corrector will obviously automatically go to the northwest direction. The spheres are in reciprocally opposite direction. So if the starboard sphere comes southeast of the compass, the port corrector sphere comes northwest of the compass. So this is the heading on which the correction can be done. Now there is one more possibility which is available to us, and that possibility is, instead of taking the starboard corrector sphere to southeast direction, we can also take the starboard corrector sphere to the northeast direction. That is also a intercardinal direction. So the starboard corrector sphere can be taken to the northeast direction also. Now for doing that, the sphere has to be turned anti-clockwise by an angle of 55 degrees. Northeast direction represents 045. The sphere is at a direction of 100. So it has to be turned anti-clockwise by an angle of 55 degrees. This basically means that the ship needs to swing to port. Let me show you with an arrow. You can see this red color arrow showing that the ship needs to swing in the port direction by an angle of 55 degrees. And if the ship swings to the port side by 55 degrees, the heading of the ship will be 305 degrees. So if the vessel heads 305, the starboard corrector sphere will come northeast of the compass and the correction can be done. The port corrector obviously will come in the southwesterly direction then. So both the spheres will be lying in the northeast southwest direction of the compass. So we have obtained two options. One is heading 035, the second one is heading 305. Now if you look carefully, even if the ship goes on a heading which is reciprocal of 035, reciprocal of 035 would be 215. Even on that heading, the spheres will be lying at an intercardinal direction. You see, at 035 heading, the starboard sphere was southeast of the compass. When the ship goes to 215 heading, reciprocally opposite heading, this starboard sphere will go to northwest of the compass, reciprocally opposite direction. So the correction is also possible when the ship is heading 215, and the same applies to 305 heading also. If the ship goes on a heading reciprocal of 305, which comes out to be 125 degrees, even on this heading, the correction can be done. So these are the four headings which we have obtained: 035, 125, 215 and 305. All these headings are perpendicular to each other at a 90-degree difference from each other, and the correction for combined correction for coefficient D and E can be made on any one of these headings. So the answer is obtained as heading has to be 035, 125, 215 and 305. Any one of these headings, the correction can be made.